Thanks, Cindy. And I'm going to talk today about code migration and software environments. Pretty much is a talk that is based on things that we are doing on Expanse, but it's generally applicable. So most systems that you go to will have similar setups. So let me see. That's the complex slide, which you probably all have seen before. So I'm going to supported by an NSF award. So the outline is essentially going to progressively go from the simplest options to building applications at the from source and building containers at the end. So basically, we'll start off by looking at things that are already available on Expanse or on any other systems that you access. So, for example, things in modules and containers that are already available on the system. Then we'll take a look at Python-based applications and R-based applications, how you can deal with them. There's multiple ways of doing this. And then we'll look at an example of building applications from source. So what you're doing is essentially utilizing dependencies that are already on Expanse, but compiling on Expanse, essentially. And then lastly, we'll just look at some Singularity container options. I do have a GitHub link in the slides. You can go there and look at some of the hands-on material that's there. You don't necessarily have to do that today, but if you get access to Expanse or on some other system, you can try out some of these examples later or today. I'm just going to walk it through from one of my test accounts, but the instructions are pretty simple, so you can do that later also. So let's look at what's already on the system. So a lot of times, and this is, as I said, true more than just Expanse. Most systems, there'll be a large suite of libraries and applications that already installed. Most of the NSF-funded systems, for example, the user base has matured over a lot of years, and we sort of know what kind of applications people need. And typically, most centers will have a similar software stack everywhere. At SDSC, we also have some commercially licensed software like QChem and Abacus and Gaussian that we make available through modules. So the primary approach for making applications available on Expanse is environment modules, and you can use the command module spider. And if you give it a name, it'll also look for that pattern in the available modules. So for example, if you're looking for FFTW, you can do module spider FFTW, and it will give you all the versions that are there. Some of the applications frameworks we've made containers. We typically do this if these applications are changing a lot or have like a complicated dependency tree that we can't really install very easily on the base system. We end up doing containers. And as I mentioned, this what we are looking at today, you can reuse on other systems. And the last thing, at SDSC, specifically, we are coming up with clusters that are Kubernetes based. Mostly there, you're using containerized images. So you can develop those images using the Coder environment or a GitLab plus Kubernetes development environment that we have. But I won't go into the details of that today, but I just wanted to mention that. So using module spider to find applications. So like here is an example, like if you do a module spider MATLAB, it's going to give you all the different versions. And we'll do a little bit of hands-on from my account just to show you how that looks. And the output is essentially going to give you various versions. And if you take the specific version and do a spider on that, it'll give you, if there are two different versions of the same, two different modules with the same version, it'll show you that. And on Expanse, you'll see this quite often because we have a GPU stack and a CPU stack that is separate. So there'll be some packages that might be there in both, and the same versions might show up twice. So for example, here, if you now pick one of these and do a module spider, now it tells you, hey, that's with the CPU stack, essentially. Similar thing, if you want to look at libraries like FFTW, if you do a module spider FFTW, you can see it gives you all those versions, but it's also picking up AMD FFTW. So that is like something optimized for the AMD processor. And again, if you pick one version and do a spider, it'll tell you what all dependency modules are required to be loaded. So for example, this particular FFTW version, you have to load the CPU module, the GCC 10.2, the Mbappage2 compiler, and then load the FFTW. Now, once you've done all that, if you do a show on the particular module, it'll actually give you a full description of what exactly the module is doing. And so, for example, it might be setting a library path, a path, and a man path. So I'm just going to pop out of the presentation and look at uh, one of these examples. Let's see. It should be hiding this. Okay. You can see my terminal, okay, right?
Yes.
So if I do a module spider MATLAB, you can see all the versions. And if I do a module spider, I'm going to pick an older version just so that you can see where it's coming from. So you can see there are two versions of this MATLAB 2020B, and I can either load the CPU or the GPU version. And if you do a module spider on FFTW, you'll see all the different versions that I was talking about. And then if you do a module spider, like say FFTW 215, it'll give you two versions. And then I'm going to do a spider again on one of them. And you can see now that this requires these modules to be loaded. So typically, the best way to do it is do a module reset, which gives you all our defaults, and then do the module load the dependencies that are listed, and then I can just load the FFTW 215. And if you do a module li, you can see all the modules that are loaded. So you can see there are some that we didn't explicitly load. Those are the defaults. And then there's the CPU stack and the GCC 10.2 and so on. And if you do a module show on any of these things, say, for example, if you grab the GCC and do a show, it tells you actually a lot of detail on how uh, the particular module was built. So that if there are configure options to build that package, so GCC in this case, you can see all those options. And then you can see that it's prepending some paths. Like, for example, it's changing the module path. And the reason is we have like a hierarchical setup for modules. So if you load GCC 10.2, you will see other modules that were built based on this compiler. So that's why it's appending that. So, and I'll show you how this looks if you start from scratch. And then it's prepending library paths. So basically these packages will have dynamic libraries that are needed. And so it'll prepend that path to it. And then it'll change the path so that if you do a which on GCC, you can see that it came from this path. So let me highlight it here. And so you can see it's basically picking up the GCC from there. Now, if I do a module reset, it will unload that module. And if I do a which GCC now, it's going to actually pick up the system OS version of GCC, which is an old version, right? Now, if I do a module or GCC 10.2 and do GCC dash dash version, you will see that you get the 10.2. So essentially it is changing the paths so that you pick up the new version, the loaded version first. That's why it's prepending all those paths. So if you do a module reset and do a module avail, which tells you all the available modules, and I might have frozen something. Okay, so you can see, you don't see that many modules. And if you, so in this hierarchical setup, you don't see the other modules till you load the compiler that is required. So you can see there's a compiler here. So if I load that compiler and then do a module avail, you can see there are a lot more packages, and all of these were built with GCC basically. And if you can go one more layer up and you can say, hey, I want to load an OpenMPI version. Say I do that and then do a module avail, you'll see there are some packages that were built with OpenMPI. So like in the Amber software package or HDF5 or GrowMax, all of these are applications that are built with GCC 10.2 and OpenMPI. So that's the way it layers everything. So let me go back here. And if just quickly jumping over to that GitHub site that I linked, basically it has some command sets that you can follow along later if you want to. So back to talk. All right, so we saw how the module spider gave us the loading information. And one thing to remember on Expanse, and this may or may not be true on other machines, is that the CPU and GPU stacks are completely different. And this is because the CPU type on the CPU nodes is different from the ones that are on the GPU node. So the GPU nodes have Intel processors and the CPU nodes have AMD processors. And they don't support the same level of optimization in, like, say, like the AMDs only support AVX2 and the CPUs on the GPU node are Intel ones that have AVX 512. So so if you build something on the GPU stack and try to run it on the CPU node, it's going to fail because that particular optimization doesn't exist on that CPU. So it's very important that you don't mix the two stacks. So if you need some packages and you need to get them all from one of these stacks. So if you pick CPU/17.3, find all the modules under that and not mix and match from somewhere else, because you are likely to have failures because of that. Now, if you say that, hey, I needed this dependency, it's not existing in that module list there for that particular CPU stack, you have two options. You can ask us and we can see if it's easy to build it in, or you can build from source in your home directory. That works too. And we'll see some examples of that. Now, going on to containers, and let me see if I can hide this again. Some of the applications, as I mentioned, are made available through Singularity containers. And this is on Expanse, we have one location for it, CM Shared Apps Container Singularity. And some of the examples are TensorFlow, PyTorch, AlphaFold, and so on. And we also have the Extreme Scale Scientific Software Stack. This is a container that has a lot of the optimized math libraries and a lot of standard dependencies that scientific applications need. And this came out of the Exascale project, so they have they maintain essentially optimal combinations of these libraries. So a lot of times these math libraries might have interdependencies, and they are essentially qualifying and optimizing them. So that container is actually useful if you're trying to do scientific application builds. Um, so, but why containers? Basically, if you have a baseline OS, like for example on Expanse that we have Red Hat, sorry, not Rocky Linux 9, I think right now. So if you want to install other packages into that, sometimes you may have conflicting stuff that we can't change, or you have a dependency tree that requires a lot of compiling and building, and that can turn into pretty complicated installs just from the point of view of managing them and keeping them consistent with all other applications. And we have to retest all our applications when we do major changes because we don't know, something that works for one code might break something for another code. And some of these applications that we have listed, like TensorFlow, PyTorch, and AlphaFold, they are driven uh, uh, by industry, by academia, all together kind of pushing it quite hard to come up with new versions very quickly. And often the new versions are not completely backward compatible and they need dependencies that are different and so on. So you end up having to do complicated installs. So instead of doing that, we end up using a container. And I think Bob replied on that question. Essentially, the container has all the you can have a different OS completely. For example, you can run an Ubuntu container, and all the libraries could be completely different, and that whole environment is encapsulated in the container. So it makes it easy to uh, update things and keep consistent dependencies together. Uh, and usually it all works fine as long as a few caveats, with a few caveats. Basically, one is the kernel that you require should be compatible with the underlying kernel that's on the system. Uh, Usually that's not a big issue because with kernels, I think a lot of stuff is backward compatible, and unless there is a new feature that's completely unsupported on the old kernel, you'll usually be okay. Uh, and the other is if there are drivers that are underlying your particular container requirement. Like for example, if you're installing CUDA in the container and you pick the latest CUDA version, and that latest CUDA version is not compatible with the driver that's sitting on the system underneath, then you'll have issues. So you have to make sure of those two. But other than that, you can essentially be very flexible with what you install within a container. And Marty, who's I think on the call, basically maintains the Singularity definition files for everything that we have installed. So you don't, so for example, if you see a container on SDSC's list and you say, hey, I want to add a few packages to PyTorch, you can go to his definition file and then, or just use that container as a starting point and layer in what you need on top of that to build a new container. And running jobs through containers is reasonably simple. So if you look at a Slurm job script, for example, I have here an example that's using a PyTorch container. And what we are doing is using one GPU in a GPU shared partition. So all of this looks like a normal Slurm script. And the only thing we do is we reset everything and only load the Singularity module because we don't want to pull in an environment from outside the container that is conflicting with what's in the container. So we reset all that and basically load the Singularity one and module, and that lets you get the Singularity executable, and you can execute your script, say in this case a Python script, in the Singularity environment. Two things here. In orange, I see you see the dash bind slash expanse comma slash scratch. What this does is essentially pulls in those locations, file system locations, into the container. So it bind mounts it. And you can bind mount in the same location. For example, here I didn't actually give the location to mount it on, so it will just mount it in the slash expanse location. Or you could actually put it somewhere else. For example, sometimes containers might require inputs at a particular path. You can take your input directory and mount it on that path. So the bind mounting has some flexibility. And then we are doing a dash NV. What this does is pulls in the driver info from the system underneath. This is mainly for the GPUs, the NVIDIA drivers. And then the next part in green is essentially the container that has all the environment for PyTorch. including Python and all the libraries that are needed. And then we run Python. So basically what happens when you do this is it's going to have these directories in the container, pull in the driver, and run your Python script using the environment that's in this container. And the overhead is pretty minimal. In fact, sometimes the containerized versions might run a little faster because the entire container sits in memory. Uh, so all the file system access in the container, the container contents will be in memory. So it'll be a lot faster than, say, you have a conda install in a home directory. You might be subject to the load from other people. So you might see actually sometimes slightly faster runs there, uh, especially if there are millions of small files in your install, then that can actually do better with the images. So I'm going to just show you, you can still see my screen, right? And I'm going to copy commands from here. So I'm copying the PyTorch example. And if you look at the run script there, it's running on the CPU node, asking for shared partition and loading the Singularity module and running the example essentially. So I'm going to use a different account here. You can use your own account. And I'm also going to change the partition because I think I'll get through quicker in one of these other partitions. But you can use the regular shared partition that's in the script. So you can see that the job is running already. And if you look at the PyTorch module, it's loading all those. That's the environment, and it's going to start. If you look at the script, it will actually download the data, and it'll be in /scratch. So we can actually go look at it there. So one thing is on Expanse, when your job is running, you can actually go to the node that's running a job. So I can go there, and you can see that it's downloading the data and so on. So it's going to run PyTorch, and we don't have to wait for that, but I just wanted to show you. All right, so back to this. You can see my full screen again?
Yep.
Okay, great. So that's the simplest thing. If the application you need already has a module or it has a container and it's sitting on Expanse, you just run. Then next we'll take a look at Python and R specifically. Lots of different ways of doing it. We do have modules for Python applications, but one caveat here, we don't update these as often. So if you're looking for updated versions, it's best to use one of the other options that I'm going to mention, but we do have applications and libraries via modules. So for example, you can load matplotlib or SciPy using modules. So again, you can do the same thing you did that we did before, where you do a module spider and module show to get info and then load the packages. Some of these might depend on MPI, like SCF, which is an application, I think, that needs MPI for Pi for multi-node runs. Actually will load the MPI that's needed. As I mentioned, if all the packages you need are in modules, this is not a bad option. You can just load everything and run, because especially with the MPI versions, it's best to use the system MPI. But often what you'll see is either the modules are old, or you need a package that doesn't exist in this list, and it's not that easy to install. So we end up recommending you either go the conda route, or so you can use Miniforge or Miniconda to do your Anaconda installation, or use the containerized approach. Main thing to keep in mind is you cannot mix Python libraries from the modules from one of these sources. Like say you have a conda install, and then go try to use it in a container. They'll likely conflict and fail. So whatever you do, you have to pick one of these three options. So either R modules or conda or Singularity, and stick to that for all of your dependencies. So you can do installs using Mini Forge or Mini Conda installers. One thing with to keep in mind with Conda installs is they do have a lot of small files, and they unfortunately put all of them in the path check when you initialize things. So it's a really bad idea to put this in Lustre, because the Lustre file system doesn't do very well with metadata loads. So install it in your home directory. That should be okay. Or there are other options, and you can contact us, but we can give you more details. But Marty has a setup where you can essentially install the conda install into the local scratch, and then have it bundled and stored in the location you want, and then extract it each time you need to use it. But the main thing on the GPU side is, if you do a conda install, just make sure whatever version of the package you pick works with the driver on Expanse. So for example, our current driver, and we are about to update this, but the current driver is 525.85.12, and the CUDA version is 12. So if you try to install something that needs CUDA 13.6, for example, which might happen, because if you do a conda install with the latest version, it'll just pull in whatever is the latest available version. That's may work for most part, but if there is a feature that's not supported in the old CUDA, then it's going to fail. So that's one thing to keep in mind. And when you do conda searches for packages, they typically have the CUDA versions in the description. So you should be able to, or even in the name, so you can pick the right one to install. Just keep in mind that you can't blindly install the latest version. That's all. And suggestion is you should install this on a compute node. So I'm just giving you an example. Basically, using srun, you can get to a compute node and then do the conda install. And typically, conda installations, they will have an install script that you can download or wget. And if you source that, it's going to walk you through the install process. Just make sure you don't install it on the Lustre file system. That's the only thing to keep in mind. So stick it in the home directory. One caveat with conda installs is, if you do an MPI for Pi install. So for example, if there is a conda package that needs MPI and you don't mention anything, it's just going to install a conda version of OpenMPI, which is functionally okay. It's going to run, but it's going to use the wrong network and basically will not scale that well. So if you do need MPI for Pi, this is one place where you may have to mix the external MPI with the conda-based install, so that you use our MPI, but use the MPI for Pi built with our MPI instead of getting it from conda. Similar thing for R. SDSC has a lot of R applications and libraries that are available through modules. So you can do module spider R dash to find all the R applications. Again, if you need to add additional packages, sometimes it works to do the R package additions, but it's best to go mini Forge Conda or Singularity approach if this happens. Same caveat as Python, don't mix and match from different versions. So now one example, and I'm going to show how to do this now, is we can actually get a Docker image and use it as well. So this is a code called excerpt, where there was a Docker image already available, and the user actually had pointed me to the distro, and when I went there, they had a Docker image. So we can actually build the image. The one thing to do to make sure is that you do this build again on a compute node, mainly because some of the Docker images can get quite big, and they need a temp directory, and they use /temp by default, and the /temp on the login nodes is very small. So you're going to fill up the /temp, cause your build to fail and also make a lot of people unhappy, because Slash temp being full will cause compiles to fail and all kinds of things to happen. So make sure you run this on a compute node. And you need to do this only once. Once you have the image built, you can store that image in your home directory or in your Lustre directory, it doesn't really matter. And you can reuse that image for subsequent runs. So this is a one-time thing, essentially. And another thing with R is if you do a conda install with R, don't do it on the login node, because again, it's going to basically fill up the login node completely, because what it does is it senses how many, it detects how many cores are on the node, and it tries to use all of them. And we have limits. So the net result is your conda install will hang. You can do basic checks if you want, but make sure you set the number of threads to 1, like OMP num threads to 1 before you do that, and then that is okay. So here is an example of using R through Singularity. So this is that excerpt thing that I mentioned. So once the image is built, so the module reset and the Singularity Pro module is loaded, so you get Singularity. Now in this case, notice I'm doing a Singularity run and not an exec. It's because this container actually has a default run script in it. So when you do Singularity run, it's going to just run that script. So I have this example shown because it's a little different from I just noticed that there are lots of questions. Okay, are being answered. Okay. I will stop after this and maybe check through to see if there are any questions to be answered. Okay, so the reason I have this example is because here actually the bind mounts are in a different location. So what I'm doing is there is an input directory that has to have all the inputs for the code. And excerpt actually expects the input in a particular path. It expects it in slash excerpt input. So what I'm doing is taking that input directory and mounting it there. Similar thing with output, it expects the output to go to one location, so you put it there. And then I'm binding in some data because excerpt also needs like reference data. And again, we didn't put the reference data in the container because then the container gets to be too big. So it's sitting on the system, and I just mount it on the location that it needs. And then we run the excerpt uh, script and with the input file. So I think I have an example of doing all this. So let me just go back here. And go to my command list. So let me I'm going to do the module reset and get interactive access. And I will change this so that I get to my partition quickly. So once I land on a node, I can set the temporary directory and change to that temporary directory, and let's do the build of the container. So I am building that container now. So it's going to pull the image from the Docker hub, and I hope we didn't have an issue. No, it is doing something. Okay. Usually a lot faster on local scratch, so I'm a little surprised. Anyway, maybe the network is a little loaded. So it's going to pull in that image and create the ZIP file, which is essentially the container with the whole environment. And maybe once it's done with that build, I will actually show you how it looks in the container. Meantime, I can copy that. file. So the container is made. I'm going to copy this and I'm going to make the output directory. So now we have the inputs, the outputs, and I am going to, instead of doing the run, I'm going to do a Singularity shell so that you can actually see um, how this looks. And the container that we just created. So you can see now, if I do slash excerpt output, you can see it's empty because I just created that empty directory. But if you look at the input, now it has that file. Now notice the path outside was different and it's now mounted into this location. And if I do excerpt DB and HG38, you can see that is the reference data set that I was talking about. So all of this is essentially in the container environment. Oh, and I should probably show you where the packages are installed. So like if you look at it's probably in user local, like you can see a bunch of packages are installed in the container environment. And I might have to just go look in this. Oh, it's an excerpt bin actually. So you can see all the install tools that are installed in this container. So these are all not in our standard environment, but coming from the container. So you see the SAM tools, star, bowtie, and so on. So this has a pipeline of tools that it runs through, and it also has our uh, version there. So I think I can do. I think that should work. Let's see. Yeah. So you can see there's R installed with a particular version from that in that container. So all of it is there, and then you can just run that command. And I won't run it today because it takes a while to run. But when we do hands-on, usually we run this command. So before I head off into the thing, let me see if the questions are answered.
Mahidhar, all questions are being taken care of by the team.
Okay, great. So we are good. All right. All right. Um, so that was building an image, right? Sorry, using an image, and you're still not building that image from source. You're from scratch. You're essentially pulling from a Docker image and converting it into a Singularity image. Now that works a lot of times actually. Like NVIDIA might have containers that you can convert, or some lot of applications and Bioconda and those so on. They all have like published containers that you can just use. But sometimes you have to build everything from scratch. So the first thing is, if you have source code and you want to build a package, some applications, they will have configure scripts that will just pick up dependencies based on what environment variables are set and what's in your default path. So one such example is the quantum espresso quantum chemistry code. Like you can actually uh, all it needs is an MPI and the LAPACK, BLAS, and FFTW libraries. So what we are doing is essentially loading equivalents of those. So like we are loading the GCC9 to the OpenMPI. Bliss and libflame are essentially LAPACK and BLAS libraries that are AMD specific, and then we're loading the AMD FFTW. And the configure actually looks at some environment variables. For example, it looks at capital CC for the C compiler, CXX for C++, and so on. So here we basically gave all the compilers that are GNU based. So it's GCC, G++, and G Fortran. Then you can set all the optimization flags. So I'm setting C flags as -03 and then the AVX2 optimization. Then it also looks for environment variables, and So you can set those to point to the locations of these libraries that we just installed. So one thing, when you do a module show on a particular module and on Expanse, you'll see that we actually set this home variable to say where the package is installed. So that's makes it easy to point all these library links to. And then you just run a configure, it will pick up all these locations and test it and say, okay, that looks good. And then you just do a make. So that's one way of doing the installs. The other way you can go from source is some codes will have make files. So they will let you set all these variables in a make file. Um, so it's a little simpler than the configure, but uh, uh, so if the code is not too complicated, it's easy to just change the make file to do that. So in this case, we are setting the C compiler to an MPI enabled one and setting a few C flags and essentially building using that compiler. Um, Now, if you're compiling from source, some more things to keep in mind. All GPU compiles have to be done on a GPU node, and you might know why, because as I mentioned, the stacks are different and the CPUs are different. So if you optimize based on one, you cannot use it on another. Specifically, the login node has the AMD CPUs. So if you do some AMD specific optimization and try to run that on the GPU node, it will fail, and the other way around also. So basically, you need to get interactive access to a GPU node if you're doing a GPU install. Now, for the CPU stack, the login node is probably fine because it's the same CPU on the login node and the rest of the Expanse CPU nodes. The other thing is in the previous, the quantum espresso example, I mentioned BLAS and LAPACK math libraries. There are lots of versions of those. There's OpenBLAS that provides all of the BLAS and LAPACK. There's the NetLib versions of these. The Intel MKL libraries actually do okay on the AMD nodes as well, as long as you use the core AVX2 flag. And basically, AMD has AMD optimized versions of these. So we have all of these installed on Expanse, and the reason is it's unfortunately turned out it's application dependent on which one does better. So you might have to try out a few with your application before picking one. So the other thing to keep in mind is the libraries are all in non-standard locations. You see when you do a module show, you are looking at CM shared apps paths. That's not a standard location for these libraries. If often, like if someone's developing on a standard Linux box, like say Ubuntu or Red Hat or Rocky Linux, you might use their package manager to install all the dependencies. For example, if you want to install BLAS libraries, they might be already existing packages that you can use yum install or apt-get install to install them in your Linux box. And it will go put them in standard locations, like it will put them in /user/lib or /user/lib64 or so on. Sometimes you'll see makefiles and configures and CMakes will look for those standard locations. So you might load a bunch of modules on Expanse and then run your configure script or CMake script, and it comes back and says, no, nothing exists on your machine. Like that doesn't necessarily mean it's right. You have to go look into it a little bit and see, hey, can I actually point it to the location? Which is why if I go back to that configure there, I am pointing FFT include to the include path, which is separate from user include and so on. So you may have to do changes like that when you're building from source. Especially in a makefile, you may have to do that manually to point it to the right locations. As I mentioned, the Intel compilers will work fine on AMD nodes. Just don't use the -x host flag because it doesn't detect the host correctly. But if you just use march equals core AVX2 for your flags, it'll be fine. So this example essentially uses GCC and OpenMPI, and it's actually a code repository that's open, so GitHub, so we can compile and see how that looks. So if you look at this, you have the modules loaded. So you have GCC and OpenMPI loaded. So we have that. Now let's clone the repository, and I already did that, so that's fine. And I'm going to do a make clean here. Well, is that very clean? I don't remember what. I guess it does that by itself. I want to just remove the dot. Let's see. Okay, so and you can see there are lots of make files here. So we are going to do the AVX2 one because we know the CPU has AVX2 support. So we are using that compiler. And you can see all these object files. And essentially, it will build that from source. And if you look at the CC flags, so you have $CC, the C flags that are being set, and then the -MAVX2, because we know it's an AVX2 compiler. Sorry, AVX2 supported CPU. So, and then it's essentially compiling all these C codes together and then building the application. So if I go do a make -f avx2.mpi.gcc, you can see it's using MPI-CC with the optimization. And when it comes to the AVX2 part, it should actually show up somewhere, I think. Or did I pick the wrong one? Anyway, we'll see. But yeah, it picked the AVX2 here, if you can see that. So it's essentially compiling and building that application. And if I do a -ls-lt, you can see that's the compiled version. And if you do an LDD on that, it will actually point you to all the dynamic libraries that it needs. And you can see it's pointing to the SPAC locations for everything. So we built this code from source. And by the way, if I do which MPI-CC, it will point to the SPAC version that we just used. So that's compiling everything from source. Now it gets a little bit more complicated. So in the example that I showed you, it had all the dependencies it needs in our existing SPAC-based software install that we have on Expanse. Now, sometimes it might turn out either the versions of things that we have aren't what you need, or you need to install a new dependency, and maybe it takes us too long to do that on a system-wide basis. You can always do this install in your own home directory. So on Expanse, we've been using something called SPAC. It's a package manager that makes it easy to install scientific software. And all our recipes are actually on GitHub. And so you can see how we are actually building the whole software stack on Expanse. AMD also has some performant recipes, and you can go there and check things out. And they're contributing all of these back to the main repo. So you should be able to pick a main SPAC repo and do that. So here, what I'm showing you is an example where we are trying to build an application called WASP, but it needs some other compilers. It needs dependencies like AMD FFTW with that particular compiler and so on. So instead of using our installed version, you can create this SPAC version in your home directory. And you can basically create an environment that specific to this particular package, so in this case, WASP. And so then what I'm doing is activating that and then installing a particular compiler, and in this case, it's the AMD compiler, AOCC 420. And then I'm adding OpenMPI that's built based on that 420. And then I can give it flags that are sort of specific to what we are doing. So we are adding certain launcher capabilities and Lustre file system support and so on. So it's essentially configuring an OpenMPI that is specific to our system, including pulling in external dependencies for Lustre, for Slurm, and so on. So once it has AOCC and OpenMPI, you can install that package with all the dependencies, and it will go off and install all these packages, anything it needs that are dependencies, and you will have this package sitting in your home directory. So that's one way of doing it. Now, this is obviously more complicated and will lead to a longer compile and everything, but sometimes it's needed when you don't have all the dependencies. So that is another way of doing it. The last thing I want to talk about is containers. Now, you can use containers if there are lots of dependencies that you can't easily install in the regular environment. Like sometimes even using Spark, you can't install everything that's needed because of some glibc dependency or something that doesn't quite work out in the environment. So for MPI-based install, the thing to keep in mind is the MPI in the container should match the external MPI version. So, and also the more important thing is the InfiniBand drivers in the container should match. So for GPU installs, we have to make sure the packages installed are compatible with the driver. So all of these can be stuck in the container. Now, the one caveat with building containers is that building from scratch from definition files needs root access, and you can't do that on Expanse itself, but you can build elsewhere. So you can use your laptop or desktop or a cloud resource, like we often build on Jetstream too. And then you can copy over that image and use it on our system. That's all good. Now, how does that look? So here I have an example of it's a slightly old container file, but I just wanted to show you how it looks. So Marty has the latest versions in the link that I had in the slides. So what I'm doing here is essentially starting from a baseline container that already exists, like CentOS 7.9 in this case. And then layering in additional things. So for example, here we're going to add mVapage2 to it. So we are yum installing a bunch of InfiniBand drivers, essentially. You can see that. And then we are installing some additional tools that are needed. And then we essentially wget the mVapage2 source, because this is an open source MPI implementation, and configure and make to create the MPI install within the container. So all of this would just create a container that has MPI in it. And now if you want your other packages, you could yum install some packages, or you can add in your own builds into the container. And once the container is done, you can bring it to Expanse and use it. Now, the reason we make our definition files available is because we do have the compatible drivers and InfiniBand drivers and the GPU packages in our definition files. So you can use that as a starting point and then add in what you need. So that essentially is all that I wanted to cover today. So just to conclude, basically, there are lots of different ways to get applications working and ported on Expanse. First thing is the simple one. You see if it's already there, either via modules or Singularity images. like a lot of the standard packages, we would definitely have them installed. We have an examples directory on how to use some of these packages, so you can actually go look at those too. Now, if it doesn't exist already, or if you have a R and Python setup that needs installations, you can use either Miniconda, or if there is a container available, or if you're a container you can build, you can use those. Just keep in mind that you can't mix software installations on the system with the conda-based ones or conda-based ones with the container. All of them should be separate, and you should use only one set of these. We just saw how you can build an application from source using compilers and libraries that we already have installed, or if you go the SPAC route and build it from source the way we are building it, and we have our recipes online. And we saw how you can reuse a Docker image via Singularity by just pulling and creating a Singularity image. And last thing is you can build your own containers from definition files. And just to add to that, like if you have containers, the Kubernetes clusters like Voyager, which is a machine learning capable specific cluster at SDSC, and then Nautilus PNRP, which is a very distributed Kubernetes cluster. They both use containerized environment, so you can use that as the development environment. You can basically use the containers there, and we have development environments there to basically help you develop some of these. So I think that kind of covers all that you not need know to basically uh, get started on a system with your application and get porting. Of course, each application could have its own quirks and requirements, and with all these different approaches that are feasible, especially the containerized ones, we can almost make anything work on the system using one of these approaches. So thanks, and I'll see if there are any more questions.